Welcome to lecture number 10. Today we will continue and finish the topic with periodic signals. And in the beginning, I want to show you a last thing about RMS values, and that will be the calculation of an RMS value of a periodical function with a DC offset. And after that, I will introduce the third important value. It's the rectified value. And in the end, we will have a look which value a pointer measurement device shows. In the last lecture, we calculated the RMS values for a sine function, a triangular function, and a rectangular function. And it was quite hard work. Okay, but now it could be that we have, for example, a sinusoidal function with a DC offset. Okay, and what should we do now? Do we really have to calculate the new value with our whole equation here? And do we have to repeat the calculation every time the DC offset has another value? Let's have a look what happens if we try to calculate our integral here. Okay, we have this sum and we take the square out of it. That means we can write our function like this. Okay, and you remember that if you have the integral of a sum, you can split that sum into the sum of integrals. Okay, and now let's have a look at the single integrals. The first one. We calculate here the mean value of the DC value in square. Okay, and if we do so, we will just get the DC value in square. In our next integral, there we have a sine function, and we integrate over one period. Okay, the mean value of a sine function is 0 because we have this first positive half wave and then we have the same half wave but with a negative sign, and that means that this here becomes 0. And then in the end, we know that equation. This is exactly the equation we needed to calculate the RMS value of the alternating component of our signal. And that means if we want to calculate the RMS value of a periodic signal with a DC offset, we can just calculate it like this. We take the square root out of the DC offset square plus the RMS value of the alternating component of our signal. And yeah, that's much more easy than a boring calculation of integrals. Up to now, we know the mean value, the RMS value, and there's a third important value, and this is the rectified value. Okay, rectified value. In the beginning, what does it mean if we rectify a voltage? That means that all the negative voltages become positive. And the rectified value is the mean value of this rectified voltage here. Okay, how could we rectify a voltage? Let's say we have an AC source and it's directly connected to a load resistor. And then the voltage at the source and at the load resistor will be the same for all time steps. but we want to rectify our voltage. Okay, what could we do? The simplest way is we put a diode in here. And we just want to talk about ideal diodes here. And an ideal diode is quite easy because you see in the sign of the diode there is an arrow. And a current can only flow into the direction of that current. When a current wants to flow into the arrow direction, then the diode behaves like a short circuit. But if a current tries to flow into the other direction, then the diode behaves like an open circuit. And that means for the first half wave that the current out of our voltage source, we have active sign convention there, and that means the current leaves our voltage source upwards. And then it could travel through the diode and it can travel through our resistor and produce a voltage drop there. But for the second half wave, the current wants to flow upside down out of our source, and then it can't flow through the diode because then it behaves like an open circuit. And that means we found a way to get rid of the negative voltages. And we call this here the one-way rectification. But it's a pity because we lose half of the possible power our source could deliver, and therefore there is another way, the two-way rectification. Okay, if we have our circuit here, we could add another diode. Okay, we don't win anything from that because it just has the same influence as the first diode. But if we add two more diodes like this, then we have a two-way rectification. So have a look at our voltage curves, positive and positive again. Okay, that was too fast, I know. Let's have a look in detail. So, in the beginning, when we have our positive half wave of the voltage here, then the current wants to leave the source upwards, so it would travel this way, goes upside down through our load resistor and goes back to the source. So that means at our source and at our load, the voltage is positive. But now the algebraic sign of the voltage source flips, and that means that the current would leave the source upside down. Okay, and the current would leave the source in this direction, and you see it can't travel through the diode it used the last time, but there is a new path and now the current can flow here. And the cool thing is that again in our load resistor the current flows upside down, and that means that the voltage drop at the load resistor is positive. So if the voltage at the source is negative, the voltage drop at the load resistor is still positive. Okay, and now you know how you can build your own rectifier circuit. Let's go back to our voltage signal. We saw how we could rectify a signal, and the so-called rectified value is the mean value of this rectified voltage. So that means the rectified value is calculated by the mean value of the absolute value of our original function. Let's calculate the rectified values for our known three different signals we have. Let's start with a sine wave. So that means we have to calculate this integral here. Let's have a look how this absolute value of the function looks like. And it's like the last lecture, you see here in the first half of our integral, the result will be the same as in the second half of that. And that means we can just integrate over a half period and we multiply that result with a 2. And the good thing is, in the first half wave, this is just a sine function. And therefore, now we have an ordinary integral and nothing with the absolute value function in it. Okay, we can take the primitive of sine of omega t, and we can replace the omegas with 2 pi divided by the period time. And now it's quite cool. You see, we get rid of these t's and we get rid of these 2's. And now we can put in the borders, and this leads to this expression. And now let's have a look at the first cosinus function. You see, we get rid of these 2's, we get rid of these capital T's, and therefore we have a cosinus function of p. And this is just a -1. And it becomes a +1 with a negative sign in front of it. And here the second function is a cosinus of 0, and this is 1. And that leads to the rectified value of a sinusoidal function of 2 times the amplitude divided by pi. Let's do the same for the triangular function. We have to take the absolute value of it, and it looks like this. And now again have a look, this time in every quarter of our integral will be the same result, and therefore I just integrate over 1/4 of the period length and multiply the result with a 4. Okay, there's a lot of constant stuff in our integral. I will put it in front of it, and then I know the primitive and I can put in the borders. Okay, and if we calculate this, it leads to a value of half of the amplitude. So the rectified value of a triangular signal is just half of the amplitude. And in the end, let's have a look at our rectangular signal. This is quite easy again, because if we rectify this, it just becomes a constant voltage. And therefore, our integral is super easy because we integrate over a constant value, and therefore the primitive is just t, and if we put in the borders we get this, and this is just the amplitude. So the rectified value of a rectangular signal is just the amplitude itself. And again, here are the results for our 3 different voltage shapes, and you should know these 3 values. You should know how to calculate it, but more important is that you know these 3 results of the calculations. You might wonder why we need rectified values, and I can show it to you with an example. And the example will be the classical pointer measurement device. when we have such an old device. You can buy new ones, by the way, but they work like this. We have a permanent magnet in them and it produces a magnetic field. And in that magnetic field is a small coil, and this coil is turnable and connected to the pointer of the device. And there is a return spring at this small coil, and when the device is not connected to any current, then the pointer indicates 0. And then when a current starts to flow through our small coil, then it behaves like an electric magnet and produce another magnetic field. And now we have this external magnetic field from our permanent magnet and the small field from our turnable coil. The small coil wants to rotate until its north pole is directed to the south pole of the external magnet. But there is the return spring and produces a counterforce, and therefore we will have a stable situation for our small coil and the pointer, and it will stay at a special point. And if the current is bigger, the pointer will show a higher value. Okay, and here is what I just said, so you can reread it when you go through your handout. Okay, how will a pointer device react when we have a constant current flowing through it? It's quite easy. This is exactly what I just said. We will have a position of our pointer where the force of the magnetic fields and the counterforce of the spring are in balance. And therefore we can directly read the value of the current from our device. So, and that means that in DC measurement mode, the external current is directly connected to the pointer device, or we have additional resistors, you remember from our lecture about measurement devices. What would happen if we now connect a periodic signal to our device? Yeah, the pointer wants to follow the values of the current. That would mean that the pointer goes up to the maximum value of the current, so the amplitude, and then it will go down, and then it wants to go to the negative part, but often it can't because there's a border of the device, and after that it wants to go up again and back and so on, and the pointer is too slow. If you think about our power net, there we have 50 Hertz. So the pointer wants to go to the maximum value and to the negative maximum value 50 times per second. And the pointer is too slow. It will just show the mean value of that, and this is 0. So if you have a voltmeter and it is switched to DC measurement mode, then it will show 0 volts if you connect it to your power network at home. So if you want to repair something and you want to see if you switched off the electricity, then you might get a surprise if you measure with a instrument in DC mode. It will show 0 volt, and if you touch it, then you might remember that event. Okay, so in DC mode, the pointer device just displays the mean value of the measured current because the pointer is mechanically too lazy. So what could we do that our pointer device shows us a value? It's quite easy. We just could rectify our signal. And that would lead to the situation that our pointer wants to show something between 0 and the maximum value and 0 and the maximum value and so on and so on. Same thing, the pointer is too slow to do that, and it will again show the mean value of our signal. And the mean value of a rectified signal, that was the rectified value. And therefore, the pointer device shows from the physical point of view the rectified value of our signal if it's switched to AC mode. But we are not interested in the rectified value. We are interested in the RMS value. What could we do? Before we go on, let's have a look on an experiment where I connect an AC voltage source which can produce sinusoidal voltages, triangular voltages and rectangular voltages, and I connect it to an oscilloscope which just shows the voltage curve, and I connect it to a pointer device in AC mode and have a look on the values it displays. It's interesting, isn't it? The pointer device shows 3 different values for our 3 different signal shapes, but the amplitudes of all the 3 signals have been the same. Okay, so let's think about it. What happens in a pointer device? So we start with a current which flows through it. And then we said in AC mode, the current will be rectified in a first step. Okay, and that means we now have the absolute value of our current. And then we have our mechanical pointer, and it is slow. So that means that after the pointer, we just see the mean value of our signal, and that is what we call the rectified value. But now we are not interested in this rectified value, and that is what our pointer shows from a physical point of view, but we want to read the RMS value. And what we could do is we are free what we write on the scale of the pointer device. We just could rewrite the scale that way, that when the pointer shows us a value which will be the rectified value, we just could write the RMS value behind it. And that means we multiply our measurement result with a so-called shape factor. And then we will have the RMS value. So, what is this shape factor? As you see, with a shape factor, we can calculate the RMS value if we have the rectified value. And that means that we could calculate this shape factor if we divide the RMS value by the rectified value. And you remember, we calculated both values for our three signal forms. We know the RMS value for sinus, triangle and rectangle, and we also know the rectified values of the three. And in 99% of all the cases, the user wants to measure sinusoidal voltages or currents. And therefore, the manufacturer just uses the shape factor for sinusoidal signals. Okay, and that means we can calculate this shape factor with the RMS value of our sinusoidal shape. It is the amplitude divided by square root of 2. And we divide this by the rectified value of the sinus, and this is 2 times the amplitude divided by pi. And this leads to this expression, and if we calculate the value, then we come to about 1.11. So, to sum it up, a pointer device in AC mode shows us the rectified value, but we are not interested in that, and therefore the manufacturer just writes the scale behind the pointer that way that there is a multiplication of 1.11 included. And this is the shape factor for a sinusoidal voltage or current, and therefore the pointer device just shows RMS values if the voltage or current is sinusoidal. For all other shapes, it shows a number value, but this number will not be the RMS value and not be the rectified value. But now you have the knowledge, you can just read the value from your measurement device, you can divide it by 1.11, and then you have the rectified value, and then it doesn't matter which signal shape you have.